This is SpaceTime Series 28, Episode 77, for broadcast on the 27th of June 2025. Coming up on SpaceTime, a link between Earth's life-giving oxygen and the planet's magnetic field, looking inside the planet Mercury, and the ongoing mystery of solar heating and the sun's corona. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have discovered a link between Earth's life-giving oxygen and the planet's magnetic field. The findings, reported in the journal Science Advances, shows a correlation between the ebb and flow of the strength of Earth's magnetic field and fluctuations in atmospheric oxygen going back at least 540 million years. The research suggests that processes deep inside the Earth might be influencing habitability way up on the planet's surface. Earth's magnetic field is generated by the flow of material in the planet's molten metallic outer core, a process called a geodynamo. This flow isn't stable, and it causes the field to change over time. Earth's magnetic field is crucial for protecting life on the planet. It acts as a shield, preventing cosmic rays, the sun's constant stream of charged particles called the solar wind, as well as powerful eruptions on the sun like solar flares and coronal mass ejections, from eroding the planet's atmosphere. The authors wanted to see how important the Earth's magnetic field was in preserving the atmosphere and consequently life on the planet. But before addressing the complexity of the cause and effect relationship between magnetic fields and oxygen levels, the authors decided to see whether Earth's magnetic field and atmosphere have fluctuated in ways that demonstrated a kind of link. The Earth's magnetic field is recorded in magnetized minerals. When hot minerals that rise with magma at gaps between spreading tectonic plates cool down, they can record the surrounding magnetic field. The minerals retain a field record as long as they're not reheated too severely. Scientists can deduce historic oxygen levels from ancient rocks and minerals because their chemical content depends on the amount of oxygen available at the time they're formed. And so scientists have data on both Earth's magnetic field and its oxygen levels extend over comparable ranges in databases that myriad geophysicists and geochemists have compiled. The authors of this new study say until now, no scientists have made a detailed comparison of the two records. One of the study's authors, Weijia Kuang from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says these two databases turned out to be very similar. Kuang and colleagues found that the planet's magnetic field has followed a similar rising and falling pattern as the oxygen levels in the planet's atmosphere for nearly the last 500 million years, dating all the way back to the Cambrian explosion when the first complex life forms on Earth emerged. Kuang says Earth's the only known planet that supports life, and so these correlations could help scientists better understand how life evolved on Earth and how it's connected to the interior processes of the planet. The correlation raises the possibility that both the magnetic field strength and the atmospheric oxygen levels are responding to a single underlying process, such as the movement of the Earth's continents. The authors now want to examine longer databases to see if this correlation extends further back in time. They also want to investigate the historic abundance of other chemicals essential for life as we know it, such as nitrogen, in order to determine whether they also support the same patterns. This is SpaceTime. Still to come, looking at the inside of the planet Mercury and the ongoing mystery of the sun's corona. All that and more still to come on SpaceTime. A new study suggests that the crust and internal structure of the planet Mercury are very different from anything else seen on Earth, or for that matter, anywhere else in our solar system. The new findings are based on laboratory simulations, which will help provide important measuring posts for the European-Japanese BepiColombo mission, which will begin orbiting the rock closest to the Sun in November next year. The planet Mercury doesn't give up its secrets easily. It's not only the smallest planet in our solar system and the nearest to the Sun, it's also one of the most extreme. A sun-scorched, metal-rich world with a puzzling magnetic field and lavas unlike anything found on Earth. Anne Pamir from Carnegie University says science still doesn't understand exactly how Mercury got the way it is, but each new data point helps narrow that down. Mercury's long fascinated scientists, but all we know about this planet pretty well comes from just two missions, Mariner 10 and Messenger, and both have raised as many questions as they've answered. And one of the biggest is why Mercury is so metal-rich. You see, the planet's core makes up 60% of the planet's overall volume. That compares to the Earth, whose core makes up just 15%. One theory is that because it's so close to the Sun, it was formed out of more metal-rich building blocks. Another is that early collisions simply stripped away much of its rocky mantle. But Perbius says scientists need more data, more experiments, and more modelling in order to see which hypothesis makes the most sense. And that's where the BepiColombo mission comes in. Its instruments will probe the planet's magnetic field, chemistry, and most exciting for Pommier, electrical conductivity. But interpreting that data will require something we don't yet have, a detailed understanding of how Mercury-like rocks behave under Mercury-like conditions. To bridge that gap, Pommier and colleagues have developed analogue materials which replicate Mercury's oxygen-poor geochemistry. You see, in such environments, elements behave differently than what they do on Earth, forming unusual minerals. In fact, Pommier says her experiments show that Mercury is completely unlike the Earth. Its rocks are rich in sulfur and other elements that thrive in oxygen-poor environments, forming minerals like iron and calcium sulfides which are rarely seen on Earth. To study Mercury's volcanic past, Pommier and colleagues synthesized Mercury-like glasses, artificial lavas based on messenger data, and analyzed them using high-resolution tools like Raman spectroscopy, nuclear magnetic resonance, and electron microscopy. And the results revealed a striking difference. On Earth, lava is built from silicon-oxygen bonds that form sticky polymer-like chains. But on Mercury, sulfur bonds with silicon create shorter, less connected silicon-sulfur structures, and this radically changes their physical properties. Sulfur breaks up those long chains, replacing them with shorter, less interconnected structures. The upshot is that Mercury's ancient lavas may have flowed more like syrup rather than tar. The authors then measured these viscosities, finding them to be orders of magnitude lower than Earth's, and that may well help explain the planet's surprisingly smooth volcanic plains. Mercury's magnetic field is another mystery. Although weak, it's still active, surprising for such a small, slowly cooling planet. To explore why, the authors ran thousands of models simulating the evolution of Mercury's core over billions of years. Only a narrow range of scenarios reproduced both the magnetic field observed today and the magnetic structure detected in crustal rocks that had formed 3.8 billion years ago. In these models, Mercury maintains its geodynamo by slowly growing a solid inner core, while a thin convecting layer of the outer core continues to generate the field. Pommier thinks the convecting region in the molten outer core is getting thinner, which may explain why the field is so weak today. And with BepiColombo on its way to Mercury, scientists are gearing up for a new wave of discoveries. And experiments like those conducted by Pommier and colleagues will be essential for interpreting what the mission finds. Needless to say, we'll keep you informed. This is SpaceTime. Still to come, the ongoing mystery of the Sun's corona, and later in the science report, a new study has confirmed that Earth's seasonal rhythms are changing, which is putting more and more species and ecosystems at risk. All that and more still to come on SpaceTime. Despite all the science, all the research and endless observations, there are still countless questions about the energy powering the Sun's outer atmosphere, the corona. Now, many of these questions are now slowly being answered both by a fleet of spacecraft and ground-based observations. And while there are now lots of new hypotheses, the answers aren't all there yet. The visible surface of the Sun, the photosphere, is around 6,000 degrees Celsius, but just a few thousand kilometres above it, a small distance when you consider the size of the Sun, the solar corona is hundreds of times hotter, reaching millions of degrees Celsius or higher. This spike in temperature, despite the increased distance from the Sun's main energy source and its core, has been observed not just in our Sun but in most stars, and it represents a fundamental puzzle that astrophysicists have been mulling over for decades. The most popular hypotheses today involve magnetic reconnection, in which magnetic field lines generated both deep inside the Sun and through eddies above its visible surface break apart and then reconnect, releasing vast amounts of energy in the process. Back in 1942, the Swedish scientist Hans Alfvén proposed an explanation. He hypothesized that magnetized waves of plasma could carry huge amounts of energy along the Sun's magnetic field lines from its interior out to the corona. The Sun is composed almost entirely of plasma, which is a highly ionized gas that carries an electrical charge. The movement of this plasma in the Sun's convection zone, that's the upper part of the solar interior, produces huge electrical currents and strong magnetic fields. These fields are then dragged up through the Sun's interior by convection, and they then burble onto its visible surface in the form of dark sunspots. These are clusters of magnetic fields that can form a variety of magnetic structures in the solar atmosphere. And that's where Alfvén's theory comes in. He reasoned that within the Sun's magnetized plasma, any bulk motions of electrically charged particles would disturb the magnetic field, creating waves that could carry huge amounts of energy along vast distances, from the Sun's surface all the way up to the outer atmosphere. This heat travels along what are known as solar magnetic flux tubes before bursting into the corona, producing high temperature. These magnetic plasma waves are now known as Alfvén waves, and it was their part in explaining coronal heating which led Alfvén to be awarded the Nobel Prize in Physics in 1970. But there remained a problem in actually observing these waves. Last year, a report in the journal Science detailed observations of what turned out to be the same jet of solar wind being made by both Parker Solar Probe and Solar Orbiter, implying that the Alfvén waves were keeping the jet's energy high enough to match the observations. Over the years, scientists have employed many sun-observing spacecraft to try and study the heating problem of the solar corona. One of those is NASA's IRIS mission. Drop-launched aboard a Pegasus rocket from the underbelly of a converted Lockheed 1011 airliner in June 2013, IRIS achieved first flight the following month. Its first images showed a multitude of thin fibril-like structures that had never been seen before. The data collected from IRIS has shown that the interface region of the Sun is significantly more complex than previously thought. This includes features described as solar heat bombs, high-speed plasma jets, nanoflares, and mini-tornadoes, all of which are playing an important step in further helping scientists better understand the transfer of heat from the Sun to the corona. This report from NASA TV.
Imagine standing around a roaring campfire, roasting s'mores. You feel the warmth of the flames as the marshmallows crackle. Now, back away. You get cooler, right? That's not how it works on the Sun. The visible surface of the Sun has a temperature of 10,000 degrees Fahrenheit. Backing away from the inferno should cool things down, but it doesn't. Instead, the Sun's upper atmosphere, or corona, sizzles at millions of degrees, a temperature 200 to 500 times higher than that of the roaring furnace below. For more than a half-century, astronomers have tried to figure out what causes the corona to be so hot. It's one of the most vexing problems in astrophysics. Solar physicist Bart Depontieu of the Lockheed Martin Solar and Astrophysics Laboratory says, "The problem of coronal heating was first discovered in the 1940s. The problem involves a variety of complex physical processes that are difficult to directly measure or capture in theoretical models." On June 27, 2013, with campfires blazing around the USA, NASA launched the Interface Region Imaging Spectrograph, IRIS, a space-based solar observatory designed to get to the bottom of how the solar atmosphere is heated. IRIS studies the transition region between the Sun's surface and the corona, explains Depontieu, who is the science lead of the observatory. It can track the temperature and motions of hot gas at unprecedented spatial, temporal, and spectral resolution. Most researchers agree that the corona is probably heated in several different ways. For instance, plasma waves from the Sun can rise into the corona and crash, depositing their energy there. At the same time, heat bombs could be going off. These explosions happen when magnetic fields in the corona crisscross and realign, exploding like a miniature solar flare. One of the big questions of coronal heating has been, is the corona heated everywhere at once, or is heat delivered in discrete, bomb-like events? Depontieu says, these two possibilities are very different, but the distinction can be difficult to observe. The problem is the corona is a great thermal conductor. If a heat bomb goes off, the resulting heat rapidly spreads out over a large region. Blink, and it looks much the same as uniform heating. Fortunately, IRIS never blinks. A recent observation by the observatory's spectrographs has found evidence for these discrete, explosive events. Paola Testa of the Harvard-Smithsonian Center for Astrophysics, lead author of the paper reporting the results, says, because IRIS can resolve the transition region 10 times better than previous instruments, we were able to see hot material rushing up and down magnetic fields in the low corona. This is compatible with models from the University of Oslo, in which magnetic reconnection sets off heat bombs in the corona. Testa emphasizes that other heating mechanisms may be at work too. Even so, these new observations could help tease out how much of the heating comes from discrete heating events, helping researchers sort out a decades-old puzzle of great complexity.
This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has found that planet Earth's seasonal rhythms are changing, and that's putting more and more species and ecosystems at risk. A report in the journal Science claims people have been underestimating the true impact of shifting seasons on species and ecosystems. Seasonal changes in snow cover, temperature and rainfall have all helped shape life cycles and behaviour in most species. But in the face of unprecedented changes in Earth's natural rhythms due to climate change, these adaptations are now more and more becoming out of sync. The study's authors warn that the knock-on effects throughout food webs, ecosystems and even human society could be significant. For example, a mismatch between phytoplankton blooms and the life cycle of fish could affect the health of fisheries. A new study by Norwegian and Danish scientists has found that people who walk more than 100 minutes per day have a 23% lower risk of chronic lower back pain compared to people who walk less than 78 minutes per day. The findings, reported in the journal of the American Medical Association, examine the incidence of chronic lower back pain among 11,194 people, 14.8% of whom reported the condition. They also found that those who walked faster were less likely to have chronic back pain compared to slow walkers, although that effect was far less pronounced than simply walking for longer periods of time. A new study suggests that humans may have adapted to living in a range of new environments, such as forests and arid deserts, just before they spread out of Africa some 70,000 years ago. A report in the journal Nature highlights a study of archaeological sites across Africa using modelling to reconstruct habitat suitability for humans. They found that the niche for humans began to expand from around 70,000 years ago, most notably in West, Central and North Africa, and was then driven by an increase in humans using more diverse habitat styles such as forests and arid deserts. The authors suggest that this could have helped ancient humans tackle the range of conditions they encountered upon leaving Africa, and it may help explain why the migration out of Africa was so successful. Okay, let's end the week with another UFO story. And multiple witnesses have captured footage of a UFO in the skies over a Chilean beach. Tim Mendham from Australian Skeptic says what makes this story so interesting is that large numbers of people filmed the same event from different angles.
This is a case slightly interesting than a lot of them in Chile. It's a coastal town called Antofagasta, and there was looks like a horizontal strip with a light pulsating back and forth along it, just a white light. How big the strip is depends on how close you are to it. It was filmed by a number of people from different angles, looking out across the other side of the water. And what is it? No one's quite sure. There were suggestions that it's actually the airport and something going on there, but other people said, no, you can't see the airport from here. What was it? I mean, it's one of those stories where you'll probably not know for a long time until someone actually finds out a particular mundane explanation for it.
Something that was digitally inserted into the image, but because you said it was seen from different angles, that makes me think more likely it's just something that's been refracted through different thicknesses of atmospheric layer.
Yeah, I mean, because this was what made it a bit more interesting, because it was seen by different people and filmed. And therefore, unless it's an amazing conspiracy, and of course UFO people don't conspire ever, there is something there, whether it's on the land and it's a little advertising thing, or whether it's an airport, or whether it's cars going past, who knows. It looks too solid, actually, for cars going past, I must admit. So it's one of those things which is, unidentified, as the U stands for in UFO or UAP. And will we ever know? Who knows? But yeah, you don't necessarily make that jump from unidentified to an alien intelligence. At this stage, you're probably just going to have to say, don't know what it is. Interesting that several different people from different angles saw it and they filmed it, which tends to actually makes it slightly different from a glitch in a camera or something like that. But it's very sharp as a light. It looks like a bar on a computer or something like that, on a little power bar or something like that.
It was something digitally enhanced and placed there.
Yeah, so did I. But then because it's from different angles, there are various explanations put forward. Any of them convincing? I don't know. Are there any less convincing than a UFO? Who knows? It's unknown for the time being. So it's an interesting one to look at.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.